In this video, I'm going to go through OCR specification AS paper. This is paper. This is paper 1, and it's the second half of the paper, starting off at question 23. I covered the first half in an earlier video. Okay, so the first question is about calorimetry. We've got this reaction between magnesium and silver nitrate here in this equation. The student carries out, so he gets a polystyrene cup with the silver nitrate solution in there, adds magnesium to it, and measures the temperature change. Okay. Right, what we're going to do is calculate the delta H for the reaction in kilojoules per mole for this equation here, and really we should work it out per mole of magnesium, because there's 1 mole of magnesium in this equation here. Okay, and it says we can assume that all of the silver nitrate has reacted. Okay, so the equations we're going to use for this, we need to use Q is equal to mc delta T. So Q is the heat released in the reaction in that polystyrene cup. M is the mass of solution in there, which is going to be 25 grams because we've got 25 centimeters cubed. C is the specific heat capacity of water, which you've got on our data sheet. And delta T, well, delta T we work out from here the change in temperature, which is 47.5 minus 19.5, that's 28.0 degrees C. And then what we have to do, we have to convert the quantity of heat Q released in the experiment into the delta H, the amount per mole of reaction going on there. So we want here delta H is equal to Q divided by the moles, and it should be the moles of magnesium here because we've got 1 mole of magnesium. Okay, so how are we going to work out the number of moles of magnesium? Well, we can work out the moles of silver nitrate, and it tells us that all of the silver nitrate reacts. So we've got 1 mole of magnesium reacts with 2 moles of silver nitrate. So let's do the first of all silver nitrate moles. Okay, so moles AgNO3 is equal to the concentration multiplied by the volume. We have 0.512 mole per decimeter cubed. The volume is 25 centimeters cubed. That's 25 over 1,000 dm cubed. That is equal to 0.0128 moles. So we can say from that, the moles of magnesium here is going to be half that, because 1 mole of magnesium reacts with 2 moles of silver nitrate. 0.0128 over 2, which is equal to 6.4 times 10 to the minus 3 moles. So this value is all ready to go into this equation here. We need to work out Q using this green equation now at the top. So let's do that. Okay, so Q, the mass of solution, is 25 grams because it's 25 centimeters cubed, multiplied by 4.18, specific heat capacity of water, multiplied by 28 degrees C temperature rise. That gives us a value of 2,926 joules. Okay, so scale that up to delta H by using this blue equation up here. So delta H is equal to Q over the moles of mg, which is equal to 2,926 divided by 6.4 times 10 to the minus 3. And that is equal to 4.57 times 10 to the 5 joules. So 1 times 10 to the 5 joules. Now we need to divide by 1,000 to give us in kilojoules, which is equal to 457.1 kilojoules. And now for delta H, we have to remember that because there's a temperature rise, delta H is going to be negative. So delta H, and let's give it to appropriate number of significant figures, should be 3, because all the data is given to 3 figures like that. Let's give it to 3 significant figures. So delta H is equal to minus 457 kilojoules per mole. Okay. Right. Now, at the end of the experiment, the student adds a few drops of aqueous sodium chloride to the mix in the polystyrene cup to test whether all the aqueous silver nitrate has reacted. Explain how the results would show whether it has all reacted. Well, what's going on there? If you've got any silver nitrate solution left over, any unreacted Ag plus ions, when you add chloride ions to that, so it's going to add sodium chloride, which contains Cl minus ions. It contains Na plus ions. They're obviously spectators. If you've got any chloride ions there, it will form a precipitate of silver chloride. Silver chloride is very insoluble. So there's the equation with state symbols. It gives you silver chloride, and you would get that is a white precipitate. So that's a sort of test for a chloride ion. Okay, right. Using the Boltzmann distribution model, explain the rate of reaction is affected by temperature. You provided with the axes below, which should be labeled. Right. When you're doing the Boltzmann curve, you should have on the y-axis, you should have the number of particles, molecules, whatever, and along the y-axis, the x-axis, sorry, this is the energy. This is a full mark question, this, okay? So the energy, okay. Right, so let's draw a Boltzmann curve. A Boltzmann curve would be, we'll put this, so that's at one particular temperature, okay? Now at a higher temperature, so I'm going to do this is a higher temperature. Obviously the rate of reaction is going to be faster. You're going to get a curve which is like something like that. Okay, now there is a couple of points to note here that you should put, and you should say in this your answer. Okay, so at the higher temperature, the most probable energy is there, and most probable energy of the molecules. And at the lower temperature, the most probable energy is lower. So I'd say that. And you'd also want to say that the area under the curve is proportional to the total number of molecules or particles, total number of particles, I should say. Incidentally, that's why the red curve has got to have a lower peak to keep the areas under the two curve about the same. Okay. Now, what we need to say is collision will only result in reaction if the energy is greater than the activation energy. Call that EA. Right, so let's put the activation energy in. Let's say it's there, EA. Right, at low temperature, the only molecules that can react are those ones I've shaded in blue there, okay? Whereas at high temperature, the red one, the area under the curve is proportional to the number of molecules which can react, that have got enough energy. And you can see the area there's a lot bigger. The area is at high temperature is the blue There's the red plus the blue areas, whereas at low temperature, just the blue area is shaded in there. Okay, so you need to say more particles have energy, a greater proportion of particles have energy greater than EA at high temperature. And so more collisions will result in reaction. Okay, this is question 4 about hydrocarbons. And we've got the skeletal formula of A, B, and C, and these are all isomers, okay? So that means that they've got the same molecular formulae. Well, let's look at A. What is the molecular formula? A, you've got 5 carbons. 1, 2, 3, 4, 5. It's saturated, there's no double bonds, so the number of hydrogens is going to be 2n plus 2, so it's 2 times 5 plus 2, so that's going to be H12. And it's the same for B and C, they're all C5H12. Okay, use the structures to explain what is meant by the term structural isomer. So you need to say definitely same molecular formula, in this case C5H12, but different structural formulae. Right, so we've done that bit. That's done. So that's probably 2 marks for that. And explain the trend in the boiling point. Okay. Now, looking at these molecules, you've only got carbons and hydrogens. So there are no carbon and hydrogen. They've got approximately the same electronegativity. So no dipoles, no permanent dipoles. So what kind of intermolecular forces are we going to get? We're just going to get London forces or dispersion forces. Now, the London forces are going to be bigger when the molecule is a straight chain. When it's a straight chain, because you've got more chances of points of contact, okay? More points of contact between molecules. So the electron charge cloud of molecules of A have got more points of contact with each other than they have with C, because this is kind of got a lower surface area, if you like, that molecule, with it being branched. A lot of the electrons not on the outside of the molecule, they can't interact with the electron charge clouds on other molecules. If you put down what you've got in green there, that is more than enough for the marks. Okay. Right, this question continues about these isomers. Okay, thanks. Right. Organic compounds A, B, and C all react with chlorine in the presence of ultraviolet to form organic compounds with this formula. So you've swapped a hydrogen for a chlorine. So it's a substitution reaction. What kind of mechanism it's called? We should know this is a free radical substitution. Now, complete the table to show the number of structural isomers of C5H11 that could be made from A and B. So I've drawn A and B there again, just to help us. Right. So we've got to replace. Let's have a look at A then. We've got to replace a hydrogen on one of those. We've got 5 different carbons there. So let's see if I'll draw them in a row like that. Now we could replace a hydrogen on the end carbon. That would give us 1. That's going to give us 1 isomer. Or if we put it there, that's going to be the same. That's not going to be any different, is it, than the other one? Or we could put the chlorine there instead on number 2. That would be another 1. And that would be the same as we put it there. So we've got another 1 there. And finally, we could put it on the middle one. Yeah. Okay. So we've got 3 possible isomers with A. Let's see what happens with B. Right. So with B, we have got 4 carbons in a row like that, with a branch coming off there. Now, if you look at these 2 carbons here, these are exactly the same as each other. So if you put a chlorine on either one of those, it's the same thing. So that's just one isomer. So that one there is the same. So I'll cross that out. There is a hydrogen on there. You could put it on there. That would be different. Or you could replace the hydrogen on that one. That would be different. Or finally you could replace a hydrogen on this one here. Okay, so how many different versions have we got there? Well, we've got 4 different isomers. 4 is the answer there. Okay. The reaction of a compound reacts with excess chlorine to form D, and it has a molar mass of 175.5. Right. Did draw a possible structure for D and write an equation for its formation. Right. So let's think about the molar mass of A. A is C5H12. Okay, so that's going to be, what's the MR of that? It's going to be 5 times 12 for carbon, 60, plus that's going to be 72. Right, now this is quite a lot higher than that, and I think we're going to add chlorines to that, each of which weighs 35.5. Just replacing one hydrogen with the chlorine isn't going to make it heavy enough. 2 isn't going to make it heavy enough. That's going to make it 140 odd. I think we're going to have to replace 3 chlorines. So let's just do that. So C5, now we replace 3 hydrogens, so that would be CH9 now, and 3 chlorines on there. The MR of that is going to be 60 plus 9 plus 3 times 35.5 for that, and that is equal to 175.5. So we've substituted 3 chlorine atoms there. So we've got to draw a possible structure for D. So all we've got to do, we can put the chlorines wherever we like. I won't draw it so if you want to draw it skeletally, you could just put a chlorine on there, a chlorine on there, and a chlorine on there. And there's lots of other things you could have. You could have 2 chlorines or 3 chlorines stuck to this end one, but that's probably that's certainly one option. Okay. Now we've got to write an equation for that now. Okay, so we're going to start off with C5H12, and that's going to turn into C5H9Cl. Now we do that overall, we're going to react that with chlorine in the presence of UV, and if you remember, each hydrogen that comes off on the other side, well, that joins up with the chlorine to form an HCl. So how many HCl's? Well, we're getting rid of 3 hydrogens from here, so it must be 3, so there should be a 3 there as well. 3 HCl molecules. And how many chlorines have we got altogether? Well, we've got 3 on that one and 3 there, makes 6. So we need 3 Cl2 there to balance the equation. Don't forget, the most common mistake people make here is that they forget the hydrogens that come off always end up as HCl. They don't end up as H2 or anything like that. That's wrong. It's always as HCl. That's most people will go wrong there. Okay. Right. Question about alcohols. Okay. The 3 reactions of an alcohol E. We've got E there. There we go. Complete the figure to show the structure of the organic products formed in the reaction. Okay. So, right. First of all, we're going to react with sulfuric acid and heat. If you do that, the sulfuric acid acts as a catalyst, and you get dehydration to form an alkene. Okay, how does that work? Well, you remove an OH from one carbon and a hydrogen from the one next door, and then you form a double bond between those 2 carbons. So that structure is going to look like this. We've got a double bond. We've now just got 2 hydrogens on that end carbon. We've got our CH3 group still there, and we've got a CH3 group there, and that hydrogen, of course, is gone. So you would have there methyl propene. That's that one. That's the answer there. Okay, now I copied this again because it's not enough room. Now what we're going to happen here, right? We're going to react the alcohol both times with potassium dichromate in acid solution, you're going to get an oxidation reaction there. But if you distill it, now this is a primary alcohol, and remember, a primary alcohol, if you react it first of all, to oxidize it first of all, you get an aldehyde. And if you react it another step, you're going to get a carboxylic acid. Now, if you reflux it, you get these two steps. You get the carboxylic acid. Okay, so I'll write that there. If you just distill off the product immediately, you just get the aldehyde, so you get that. So let's draw the full structure. Okay, so what's the aldehyde going to look like? Well, it's going to be most of the molecule doesn't change. But 2 methyls on that carbon. And you change this to that. There's the aldehyde. If you oxidize it all the way, you are going to get the carboxylic acid. You're going to get that. Okay. Then this question here, what's the systematic name of alcohol E? Right, let's put in the, so I should, it's the longest carbon chain, 1, 2, 3. I should call this one 1 because that's got the functional group on it. I shouldn't call it, shouldn't label it, number it the other way around. Right, so it is propan 1-ol. But we've got to remember we've got a methyl group on carbon number 2, so it's 2-methyl propan 1-ol is the answer. Okay, an alcohol can be prepared by hydrolyzing the haloalkane, this one here, with aqueous sodium hydroxide. Outline the mechanism of the reaction and show curly arrows and dipoles. Okay, so I'm going to draw this out properly rather than on one line because it's confusing like that. So I've got that carbon there, right, has got a bromine attached to it. It's got a CH3, a hydrogen there, and then you've got an ethyl group, which I'll draw it like that. Okay. Aqueous sodium hydroxide. Right, with aqueous sodium hydroxide, you're going to get a nucleophilic substitution reaction. Okay, so here's our OH minus. The sodium bit is a spectator ion that doesn't do anything. I need to draw one of the 3 lone pairs, and I also need to draw one of them because that's going to move. We need to draw a partial positive charge on that carbon, and that's because bromine is more electronegative. So that makes the lone pair attracted, and the lone pair is going to eventually move on to that carbon and form a bonding pair. That means the carbon's forming too many bonds, so the pair of electrons in this bond has got to go onto the bromine. So if we draw what happens there, you get CH3CH2. You're going to get the new OH on there, the alcohol, CH3 there, and what's left over is the bromide ion. There's our complete mechanism. Okay, so now this is the infrared spectrum for the compound we started off with. The haloalkane is shown there. Okay, and it says outline how infrared spectroscopy could be used to show the bromoalkyl functional group has reacted and formed an alcohol functional group instead. Okay, so we want to show that, I'll just write it like this, or it was a secondary, so I should really do that. We want to show that has turned into that. So we've no longer got the carbon bromine bond, that's gone, but we do have this OH bond instead. Okay, so infrared spectroscopy, it shows us in here, this peak here, that will disappear. That's pretty tricky because that, of course, is in the the fingerprint region. So like the fingerprint region, everything to the right of there. We don't normally try and assign peaks in that area to particular functional groups. It's too hard, but they've showed us that. So that peak would go. The alcohol, now you're going to start forming an alcohol. If you look carefully here, right, and I'm going to draw attention to, well, right, so that one as well. Look, the CH is in that range. So this big peak here, that is due to CH, and that's present in more every molecule you look at. So it's not actually that useful. But the OH group, sorry, that's the carboxylic acid OH group. That's not quite right. The OH group in alcohols is it's fairly broad, and it's between 3,200 and 3,600. And so it's going to look something like that. You'll get that. Right, and can you see how it's right next door to the CH peak? It's always right next door to there. It's quite easy to spot for that reason. It's fairly broad. That is what, there's 2 marks, so you just got to basically say that you'd get a broadish peak appearing in that region, and this peak will disappear. And that is the end of the paper.